For our first presentation on earthquakes, what I need you to do is take notes on a sheet of scratch paper, which you will then use to answer questions on a notes check when we're done. First of all, this concept of rock deformation. We have an idea that tectonic plates, big, huge chunks of the Earth's crust, are actually bumping up and grinding up against one another. Sometimes they squeeze together, sometimes they slide by one another. And right where they touch, that's where rock is being ground and pushed and squeezed. Now, rocks don't squeeze very well. They're not very elastic like a stress ball. But rocks under this kind of pressure can actually get squeezed together, and that stores up an incredible amount of energy. That's the concept of rock deformation. Rock deformation is the bending of rocks as plates interact. Rocks basically getting squeezed together. That leads to the discussion of what is an earthquake. An earthquake is the release of the energy when those rocks that are squeezed end up snapping. Rocks don't bend very well, but when they do, they will snap. And when they do snap, they release energy. That's what an earthquake is. And that energy goes throughout the rest of the ground, and that's what we feel as an earthquake. Now, there are two terms here, epicenter and focus. The focus of an earthquake is down here underground. That's where the rocks are actually being broken. They're being squeezed and they're being broken because that's where there's the pressure to make rocks deform. Up on the surface, you don't have enough pressure to make rocks squeeze and deform and then break. Earthquakes happen underground. They happen at the focus. Now, the epicenter, that's what we hear about on the news because that's where people are. The epicenter is the point on the surface above where the earthquake happens, that point where the rocks are being bent and squeezed and then breaking. That's where the people are. So on the news, you'll hear the epicenter because that's where people are closest to an earthquake. Keep in mind, nobody is ever really at where an earthquake happens because nobody's that deep underground where the rocks are breaking. Now, when these faults move back and forth, when they squeeze the rocks and they bend and then they break, you get two different types of motion of the ground. You get what's called an uplifted motion, where one plate is going under the other, so one plate goes up and the other goes down. You can also get it where the two plates are sliding back and forth on one another. The rocks are still being squeezed and ground together and releasing energy when they snap, but the motion of the ground is side by side. That's called offset motion. Here's an offset fault. This is an orange grove in Southern California, and you can see how the lines of the trees, they do not line up anymore because this land is moving this way and this land is moving this way. This is an offset fault motion. You can see it here, a freshly plowed field where we had an earthquake, something moved that way, something moved that way. Now the lines in the field don't line up. You can see it here. This was about 10 feet that this fence was offset during the San Francisco earthquake in 1906. This road here used to be straight, but now part of the land moved this way, part of the land moved that way, or vice versa, and that's an example of an offset motion at a fault. Now, you can also go up and down. This is uplifting, and you can see how this fence, or that chunk of land, was pushed up. You can see it here too. This drainage here was together before the earthquake happened, before the fault moved. And the land here went up. Maybe this land went down. And you can see there is a vertical motion of the land. That's called uplifting. Now, the San Andreas fault is one we're going to reference a lot. And it's the most well-studied, most famous fault in the world. It is in the state of California, and it's also one of the most active faults, and it's one of the easiest ones to study because it is doing a lot of stuff all the time. Now, how do we know that this fault is moving so quickly?
So here's Wallace Creek coming downhill, and we would expect the creek to run that way and go straight out to the lowest point, but it doesn't. You'll notice right here, the creek takes a hard right-hand turn before going straight to the lowest point. And that's because this side of the creek that I'm standing on is on one side of the San Andreas fault, and that part of the creek over there is on the other. And we're having a movement at the fault. The land I'm standing on is now moving this direction. That part of the creek over there is moving the opposite direction. So the creek has this hard turn in it because one side of the creek is moving one direction and the other side is moving the other. And this is how we actually know how much and how fast the San Andreas fault is moving. we can come out and look at, well, how far has this creek been curved? And that'll tell us an age and a how long and a how fast the land is moving, which makes Wallace Creek one of the most studied places here on the San Andreas Fault.
We also want to study a lot about the San Andreas Fault because it's in California. A lot of people live in California. A lot of people have earthquakes because of this fault.
So let's talk about fault creep. And if you remember from our discussion of erosion, we know that creep is that slow movement of sediments. Well, fault creep is the same thing. It's the slow motion of faults past each other. It's not a case where the faults get snagged on each other and then they snap and move a lot at one time. They're just kind of slowly sliding past one another. And that's what we have happening here. I'm in Parkfield, California. You can see the sign behind me. I'm standing on the San Andreas Fault. I'm actually in the North American plate right here, but on the other side of this bridge behind me is the Pacific plate. And these two faults are constantly, slowly moving different directions. Well, that means this bridge right here, where this side of the bridge is on the North American plate and that side of the bridge is on the Pacific plate, are actually moving opposite directions. And you can actually see this in the bridge. You'll notice how the bridge, the guardrail, has a curve in it because that end of the bridge on the other side is moving one way and this side of the bridge is moving another. And that's a good indication of what we call fault creep. We didn't have a big earthquake where the ground snapped and broke this bridge in half, but we can see how the land is slowly moving different directions. So once again, it's an example of fault creep. So here in Parkfield, California, where that fault creep is happening constantly, they've erected these two stone monuments here, one here and one back over here, which look like puzzle pieces that were originally together. And the distance between them represents how much this fault has slid or creeped over about the past 90 years.
So fault creep is that slow motion of faults. Now generally, you don't usually have earthquakes along faults that are creeping because they're slowly sliding past one another. They don't build up enough squeezing energy in the rocks to where they snap. Now, do we have faults here in Georgia? The answer is yes. We have the Brevard Fault that goes through North Georgia. It doesn't provide us with a lot of earthquake activity, but there are places here in Georgia where we have a place where the land has been moved along a fault. Now, here's a case where you can actually see some of that fault creep. This sidewalk in Hayward, California, you can see isn't a straight line anymore because some of the land is moving one way and some of it's moving another. All over the town of Hayward, California, which is along that Hayward Fault, that San Andreas Fault in California, things are constantly moving and shifting. And you can see these two curves don't line up anymore. Same thing here. This is in a park. Park's been there a long time, and over the past 80 years, the walls don't line up anymore. This is actually a pretty new construction. You can see how it's got a crack right here because some of the land's moving this way and some's moving that way. So you don't get earthquakes, but you still get damage from fault creep. If you have a building that sits across a fault and it is slowly moving, well, the house is going to get stressed and it is going to crack, and eventually the house could fall apart. In the town of Hayward, they got this beautiful Art Deco City Hall right here, and it is now condemned. People can't be in the building because it is being stressed and cracked and being broken apart so much because it's half on one side of the fault and the other half of the building is on the other half. Here's creep in a water tunnel. They went in and they see here that these lines in the water tunnel don't line up. Well, the water tunnel is being stretched or being pulled apart. So this is something that you've got to consider because the water pipe is going to break. The University of California at Berkeley, their football stadium is built right across a fault called the Hayward Fault that is notorious for its creep. And so the stadium, half the stadium is moving one direction, the other half of the stadium is moving the other. Well, obviously that's a problem. They have cracks all over the stadium. They've got big gaps where the concrete walls are coming apart. And they've had to go back and reinforce and rebuild the stadium so that it can flex some with the movement of the fault. Now, how are these earthquakes detected? How do we measure? How do we quantify what they're doing? First of all, earthquakes send out seismic waves. That's the transfer of energy. When those rocks break and they snap and they release energy throughout the ground, that's what's called a seismic wave. It's a push. It is a transfer of energy. You would feel it because as energy comes through something, you feel a motion. That's what the earthquakes are that we experience. Now, how do we measure these? Well, those seismic waves cause the earth to move a little bit. They cause vibrations. Well, these vibrations can be measured by a device called a seismometer, or you can call it a seismograph, even though more correctly that's the actual printout of what you get. So a seismometer will measure when the ground shakes. Here's how it works. In its simplest sense, basically you have a very heavy weight with a pin on it, and it is suspended. So it doesn't bend too much, but the roll of paper will shake back and forth as the earth shakes. Well, the pen stays in place, so it makes a mark on the paper when the paper is moving. And you can see from a paper like this, here was a case where the ground was moving. Here's another case where the ground was moving. Over here, the ground was not moving. So this was no earthquake here. This is the shaking of the ground when an earthquake happened. Now, we have seismometers here in Georgia. We have seismometers all over the world. They all talk to each other, and they measure where the ground is shaking. Through Georgia Tech, they have seismometers located all over the state of Georgia, and if an earthquake happens in Georgia, they will detect the shaking of the ground. Now, how do we quantify this? How do we describe it? Yeah, we got shaking of the ground, but how do we say this one is bigger than that one? Well, we use what's called the Richter scale traditionally. The Richter scale basically described an earthquake by how much did it make the ground shake like an explosion of dynamite or TNT. So the earliest way to measure earthquakes was to compare it to an explosive power of dynamite, which would obviously shake the ground. Now, this is not a very good way to measure earthquakes because earthquakes are a lot more powerful even than the biggest amount of dynamite you could ever possibly set off at one time. But it's stuck. And this is what you hear about in the news media when they have a earthquake in California. They'll say, oh, it measured 5.0 on the Richter scale. But this is a scale that is not used by scientists anymore because it's not very scientific. It's outdated, and it doesn't really give you a true picture of the kind of damage that would be caused by one earthquake versus another, which is what we really care about. The Mercalli intensity scale is the scale that is more commonly used now. It's a little bit more descriptive, and it's a lot like the Fujita scale is with tornadoes. Remember, the Fujita scale described the kind of damage you would expect from tornadoes, which is what you really care about. The Mercalli intensity scale does the same thing, and it uses Roman numerals from 1 to 12. And a 1 means a pretty small earthquake. Nobody felt it. Yeah, the ground did shake, but you and me didn't feel it at all. On a Mercalli scale of 2, only people who were sitting still could feel it. 3 or 4, if you were in a house, because this house is going to transmit the shaking a lot more, only people inside would feel it. Now, this is a much better scale to describe what happened as a result of that earthquake, because we really can't compare it. We don't know anything about some number of tons of TNT, but we do know what it feels like. Well-built structures slightly damaged. Well, okay, an 8 means we had a little bit of damage. Poorly built structures suffer major damage. So the Mercalli scale is used a lot more commonly now because it tells you something about what the earthquake did and what kind of damage it would have caused and how you would have felt the earthquake, which is a lot more descriptive than something like, hey, it was equal to 150,000 tons of TNT. That doesn't tell you a whole lot about what you experience with an earthquake. Now, foreshocks and aftershocks. These plates are big and huge amounts of mass, and they don't all move just all at one time. They kind of catch and snap and then kind of bounce around a little bit. You can have what's called a foreshock and an aftershock, and these are releases of energy from those squeezed together rocks either just before or just after earthquakes. They're usually much smaller than the main quake. You have a big, huge snap and a release of energy, but then you still get a little bit of energy kind of vibrating around. It's kind of like when you were to hit a snare drum and you get that first big sound, but then you still have a little bit of vibrations left over. That's like an aftershock. And these can occur hours or weeks before or after the main quake, and they're actually very useful to help predict when a quake's going to happen or if a quake is truly done or not. So next time we're going to look at what do we do to keep ourselves safe from these earthquakes and what kinds of damage do they inflict. For now, we're going to take a short notes check on the information from this presentation here.